Okay, so it's on learned planning models, and chairing this workshop, actually, I have the impression that this is the topic that's most widespread in terms of reliable data-driven planning. So most people, when they think about it, seem to think about learned planning models. And so actually most of the rest of the workshop today will revolve around that topic, and I'm happy to sort of hand over to Pulkit for a first technical talk on this.
Thank you. And hello everyone. So I'm Pulkit, and I will be presenting about differential assessment of black box.
Can you do something about your sound? It's very strange, at least at mine.
Oh, I can probably get an earphone. Give me a second. Is it better now? But somehow I can't hear you in this.
Yeah, I was muted.
Yeah.
Sorry, much better.
Okay, great. Okay, so yeah, so hello everyone. I'm Pulkit, and I'll be presenting the work differential assessment of black box AI systems. And this is a joint work with Rashmit called Nayyar and Siddharth Srivastava. So now we have seen a lot of taskable AI systems that can carry out user assigned tasks. And assume that you have such a black box AI agent that can even adapt and update its behavior. And also, you know, it's working or its model at some past point in time. And now how do you determine if it is still suitable for a task or even safe to work with after its internal working has drifted? So at a very high level, this is the problem we are focusing on in this work. Now with that, let's focus on the specific setting, which I'll use as a running example in this talk. So here we have this researcher Alice, who just purchased a new robot to assist her in the transporting of samples in a lab to various locations. And the robot came with a description of its initial internal model. And after she trained the robot to work with her, the robot adapted its model to better suit her requirements. And at some point, she notices that the robot is not navigating as she is expecting it to. And it is based on her initial knowledge of the internal working. And now she is wondering if the robot will safely carry out the task that she assigns it. So essentially, we have this setting where we have this robot with a known initial model of its internal working. And the robot came with this model, or we learned this at some point in time. Or like any other method, but it's not really relevant here. The only important thing here is that the user knew this model to be correct at some point in the past, and now the robot has updated its behavior due to some agent update event. So we must learn the updated model of this robot. And to do this, we introduce this differential assessment of AI system called DAISY. And this system collects sparse observations of the robot performing actions in the environment. And it then uses the known model from the past to predict what portions of the model may have changed due to robot's behavior update. And now to know how exactly the predicted portions of the model have changed, DAISY poses queries to the agent, and the agent responds to these queries using its updated internal working. And it can even use a simulator to do so. And this query response cycle is repeated until DAISY correctly learns the correct forms of the parts of the model that it predicted to have changed. And this updated model is then sent to the user, who gets an understanding of how the model has changed in the robot's model. Now there are two key challenges in this approach. The first one is to identify what portions of the model have changed based on a few sparse observations of the robot's behavior. And once we learn or predict this information, the second challenge is to identify how exactly those portions of the model have changed. And we do this like using an active query response interface. But before we dig deeper into these challenges, let's first see how we represent these models that we have been talking about. So in this work, we use script-like models because such models can be easily translated into interpretable descriptions. And here on the right, you can see such a model. And I guess to this crowd, I need not explain like the details of what preconditions and effects are. But essentially here we have this pick sample action, and it has the precondition hand empty and on shelf. And the effect is that after executing this action, the hand is not empty anymore. The sample is not on shelf, and the robot is holding the shelf. Holding this sample. And such models have advantage that they are clearly predictive, and they also allow interventions and assessment of causality, and that we show in a different work. But one of the major problem is that there are too many such models possible given a set of given a set of predicates and actions. So it can get very difficult to predict what portions of these models have changed based on a few sparse observations. But before I talk about that, I'll first show what we mean by a change in the model. Yeah. So as you can see, we have these literals as part of conjunctions in precondition and effect of actions. Now, any of these could change from a positive literal to a negative literal or vice versa, or they can be completely dropped from the precondition or effect. Also, any other literal can be added to the precondition or effect of any action, right? So like we categorize the impact of these changes in the model into two broad categories. So as you can see, we have So the first category of the changes is the one that leads to an increase in the functionality of the robot or the agent. So here, for example, we have this robot that takes a sample from the lab to the warehouse by first going to the factory and then going to the warehouse. Now, assume it updates its behavior due to some update event and can now directly traverse from the lab to the warehouse without going to the factory. And this increase in the agent's functionality can be captured by an observation of it executing that move action from lab to the warehouse directly. So here by observation, it's just like one or more observation traces of the form state action and state tuples. So for this case, we have this situation where the robot is at the lab and it executes move lab warehouse action and ends up at the warehouse. And there are many approaches that learn the model of an agent using such observation tuple, but they miss out on one very important drawback of learning only from such observations. Like they cannot learn about the cases where the functionality of an agent has reduced. So consider the opposite case of what we saw earlier. Assume that this robot has the functionality to move directly from the lab to the warehouse. Now, after the agent gets updated, it cannot move directly from the lab to the warehouse, and now it has to go via this factory. And in this case, we will only observe that the agent executes these actions, move from lab to the factory and then move from factory to the warehouse. And it is not trivial to learn from observations that the functionality of the agent is reduced, because what they are going to see is that, okay, the robot executed this particular action of moving from lab to the factory, and then another action of moving from factory to the warehouse. Now, since I have explained you guys this setting, now given this setting, we can easily see that there was a better way to go from like an optimal way to go from the lab to the warehouse, and we are able to do this because this is a very small state space, right? But what we are trying to figure out is that can we use such intuitions about optimality to learn about the reduced functionality? And no surprises here, like the answer is yes. So to achieve this, we place the robot in this optimal planning mode and then collect the observations, right? And in this whole work, the optimal planning mode is needed just for detecting this reduction in functionality. So we collect these observation tuples from the agent and convert them to planning problems. And we can use this for any set of states that are part of the same execution trace and are more than like one action apart. And if you remember, we also had access to this known model of the agent from the past. So we solve this planning problem using this old model to generate an optimal plan. And now if the length of the plan using this older model was shorter than the one generated by the drifted agent, then it is clear to us that the agent was able to do something more optimally earlier than what it can do now. Hence, some of its functionality has reduced. So specifically something related to the actions that were in the plan generated using the older model. And now one or more of that actions in that older plan are now not applicable. And that's why the agent is taking longer paths. So this whole analysis of increase and reduce functionality helps in solving the first challenge. And we combine this knowledge to predict specific parts of the models that may have changed. And it is possible that we predict only some parts of an action has changed, or we may only be able to tell that something in that particular action has changed, but not sure what exactly. So we assume the complete action may have changed. And here you guys can see plus, minus, and phi. And it just represents that we do not know their correct form because they may have changed. And please refer to the paper to know how exactly we figure these out using the observations. But now that we know what portions of the model, or specifically what tuples in the model may have changed, we move on to the next challenge of identifying the correct form of these tuples, like it is either plus or minus or phi. So we developed this hierarchical query synthesis algorithm that starts with a partially known model and tries to fix the correct form of each predicate one by one. So here for this example, we assume that the model contains only one action pick samples, and it has just two predicates, hand empty and on shelf. And Daisy has predicted that on shelf in the P condition and hand empty in the effect may have changed. So we pick one of these in the random order. So I'll pick on shelf, and then we create three models, MA, MB, and MC. And we do this by adding on shelf in three possible forms, like one in each of the models. We then pick two of these models at a time and generated a distinguishing query. And we do this using one of our previous work from RDDPS'21 called AIA. Okay, so here by a query, we mean a pair of initial state and a plan. And asking this query to an agent means asking what will happen if the plan is executed by the agent with its internal model as the particular model like MA or MB. And this is done in the initial state given in the query. So in that initial state, it has to execute the plan. And the response to this query is the length of the prefix of the plan that can be successfully executed by the agent with this model, and the final state that it end up in. So this query generation has the property that an answer to this query by these two models will always generate different responses. And once we get this query, we pose this to the agent, and it responds using its internal model or simulator. And then we check the consistency of the agent's response with that of these two models. And based on that, we prune out the inconsistent model. Yeah, and then what we do is we pick the next two models and repeat the same process all over again till we learn the correct form of all tuples that Daisy predicted to have changed. And there are some optimizations here and there, and you can refer to the paper for the exact detailed algorithm. Okay, now let's see some approaches that solve problems that are similar to ours. And there is quite an extensive work on learning models of agent behavior from passive observations. And the prominent ones include ARMS, SOCUM, and PHAMA. But these methods are susceptible to unsafe model inference, right? And we then have curing approaches like AIA that solve this issue, but then it will have to learn the model from scratch, right? If anything gets updated in the model. And then there is some work on model maintenance using particle filtering and model reconciliation using search in space of possible models. And these works address the important issue of bringing two models closer to each other so that they can correctly explain like the same set of plans. but they assume availability of the updated or target model in some form, whereas our approach can work with black box systems too. And now let's see how we evaluated this approach. So for the empirical evaluation of this approach, we start with the agents initialized with the IPC domain models, and then we modify some parts in them randomly. We then generate observation traces using the updated agent and use DAISY to learn the correct model. We evaluate the performance of this approach by increasing the amount of drift in the updated model and see how it affects the accuracy of the learned model and the number of queries. The size of the number of observation traces does not change as we increase the drift. So for all the experiments, we use the same number of observation traces. And here are the results. I highlight the result on Termes domain. And since we do not collect more of observations as we keep updating the model, we see a drop in the accuracy as we increase the amount of drift. So for Termes, here we collected 10 observations, meaning like 10 state action state tuples. And for a model that was half drifted, we were able to learn 78% accurate model with just 23 queries. And for the case when just 20% of the model has drifted, we were able to learn a 90% correct model with just 21 queries. And this is very less as compared to the 134 queries needed when we learn the model from scratch using AIA. And next we compare the number of queries asked by AIA to learn the complete model of the agent with the number of queries that DAISY took to learn the model of the agent that has half changed, meaning like it got drifted by 50%. And here, as you can see, AIA takes up to 5 times more queries than DAISY in almost all the cases. And to conclude, we propose a novel method for differential assessment of black box AI systems that have drifted from their previously known functionality. Our system DAISY is able to learn highly accurate models of functionality of the agent using a significantly lower number of queries as opposed to relearning from scratch. And we next plan to extend this work to stochastic settings and models. So that's all for my presentation. In case you have any queries, feel free to ask now or drop us an email. Thank you.
Okay, thank you very much. We can take some time for questions, so please. Okay, if nobody wants to ask a testing question, I can ask. Can you stop